This third lecture on magnetic vector potential. Today we shall apply the theory of vector potential for the calculation in simple cases. Note that the vector potential is given by the vector potential due to a distribution of current is given by mu 0 I upon 4 pi. If the conductor is a closed conductor, then this is dr prime by r. This is for one dimensional wire. As in first example, we consider a straight wire. We consider a wire carrying a current I, a steady current I, and we are to find out the field at a distance from this wire. We assume the wire to lie along the z-axis. As usual, we assume the wire to lie along the z-axis, and the field point is assumed to lie in xy plane. The field point is assumed to lie in xy plane. So this is the field point. In cylindrical coordinate system, it will have coordinate rho, phi, 0. So this is a field point R, and the field coordinate is OP. We consider a element current element dr prime, which r prime is q. So the field point is OQ is equal to r prime. Since it lies on z axis, it is equal to k cap z prime, which readily gives dr prime is equal to k cap dz prime. The source coordinate OP, field coordinate OP is this, is equal to rho prime rho. So the relative coordinate R is simply and the magnitude of R is z prime square plus rho square root. Now the magnetic vector potential at P due to the current element I dr prime is dA at point P is equal to mu 0 I upon 4 pi dr prime by r. If we substitute the values of r prime and r, we get this is mu 0 I upon 4 pi k cap dz prime by z prime square plus rho square to the power half. So the total potential at P is having the coordinate R is obtained by integrating of this over straight wire. So the things becomes k cap mu 0 I upon 4 pi, then now the limit, if the wire is assumed to extend from minus LA to plus LB, if we assume the wire to extend from minus LA to plus LB, then this is the limit. If we try to integrate this out, let me perform this integration. dz prime z prime square plus rho square to the power half. This is equal to rho sec square theta d theta by rho sec theta, where we have used z prime is equal to rho tan theta substitution. So the result is integration sec theta d theta, which is log sec theta tan theta. Now in terms of z, this becomes in terms of z, this becomes log for this tan theta is if we take rho common, this is so with this we get the expression for this k. The field is alone k cap mu 0 I upon 4 pi. Then this is limit z prime square plus rho square by rho plus z prime by in the limit minus LA to plus LB, which is equal to in the numerator we will have LB square plus rho square plus LB, and in the numerator we will have LA square plus rho square minus LA. This is in general the magnetic vector potential at a point P, which is at a distance rho away from the conductor, the straight current carrying conductor. We see that the as the wear becomes infinite, that is LA and LB tends to infinity, the vector potential diverges. Still we know that the curl of vector potential, that is the magnetic field due to an infinite state where has a finite value, but the vector potential doesn't have any finite value. We consider a symmetric wear, that is to say, for a symmetric wear we set LA is equal to LB is equal to L, and we assume the wear to be extending from minus LA to plus LB. So for a symmetric wear, the vector potential for a symmetric wear, vector potential becomes A is equal to this is the vector potential. If we want to calculate field from it, magnetic field from it, we must differentiate, perform the curl of it. So the BP This the magnetic field at this point is the, we write in cylindrical coordinate the curl is given by rho cap, rho phi prime cap, set del L rho, del L phi, del L z. The components are 0, only a z component survives. We call it z, where a is equal to mu 0 4 pi log of this thing. So we find that the field rho component is 0 because a is a function of rho only, so this differentiation gives 0, so there is no rho component. If we consider the z component, it is 0, only the phi component survives, and this rho cancels, and phi component is, for phi component we will have this on this, and so there is a minus sign del A del rho. The expression of rho is available. A is equal to mu 0 I upon 4 pi log of L square plus rho square plus L by L square plus rho square minus L. So del A del rho is equal to for this part. In the numerator we will have L square plus rho square by plus L, and in the numerator we will have rho times L square plus rho square to the power minus half. And for this term we will have rho times L square plus rho square to the power minus half is taken common, so that the quantity in the numerator will be this square minus this square, so this is L square plus rho square minus L square, and we will have in the numerator this rho square plus L square minus L minus rho square plus L square minus L. So this cancels out, this is minus 2L, and this is equal to rho square. A minus sign will be there, and this you see, if we consider this angle, the angle that P is obtained at the upper end, then the sine theta is simply L by this thing. So it is the field, that is to say, if we this angle theta, if we have theta, this much is L, this much is rho, so this much is L square plus rho square, so sine theta is Sin theta is L upon L square plus rho square. So this is basically the sin theta part, and to which actually makes you the field exactly same as we obtained earlier using Biot-Savart law. Another interesting property is that although the vector potential does not exist for infinite wire, but we can make some approximation to find out the vector potential for a very long wire. So for very long wire, what we do, we assume that for very long wire, L is much greater than rho. So we can approximate this vector potential at P for long straight wire. We will have k cap mu 0 I upon 4 pi, then log. In the numerator we take L common, so the L comes out from here and here, which cancels out, so this becomes 1 plus rho square upon L square to the power half minus 1, and in the denominator we will have so this is plus 1, this is minus 1. If we expand this in binomial series and apply this theory, then this approximates to this 1 plus 1 makes it 2 plus rho square upon 2L square, and this one cancels out, rho square by 2L square. So this is equal to k cap mu 0 I upon 4 pi. We will have rho square, and in the denominator we will have 4L square plus rho square. Even here another approximation could be made. If we assume that rho is much smaller than L, then we can neglect. So another approximation is this: k cap is equal to mu 0 I upon 4 pi, and we neglect rho square in presence of L square, so that this quantity becomes 2L by rho whole square. So this is equal to k cap mu 0 I by 2 pi ln 2L by rho square. 2L by rho. This is the alternative expression for vector potential for long wire. Still, if you put L tends to infinity, this diverges. Now, as the second example of the application of vector potential, we consider two parallel state wires carrying current in opposite direction. Carrying current in opposite direction. Let me write this as 4L square by rho square. So this is k cap mu 0 I upon 4 pi ln 4L square by rho square. This is the field for a very long wire. We assume that two straight wires, each carrying current I, two state parallel wires, each carrying current I in opposite direction, and what is the field or vector potential at a point. So we will have two wires. where 1 carrying a current I in the upward direction and where 2 which is carrying current I in the downward direction. Our aim is to find out potential. We choose the coordinate system in such a way that this is the z-axis, the where 1 is along the z-axis and where 2 is displaced along y-axis. So we want to find out field at a point. This point is assumed to lie in xy plane, so the coordinate is this. This is where number 1, this is where number 2. If we call the distance rho 1, then rho 1 square is equal to x square plus y square. And if we call this distance as rho 2, then this where is displaced along y-axis, so this is at r, this distance is r along y-axis, so rho 2 square is equal to x square plus r minus y whole square. Now what will be the vector potential over here? Vector potential over where at P will be the vector sum of the potentials due to the two currents. So the expression is k cap mu 0 I upon 4 pi for where 1 this is log 4L square by rho 1 square, and for where 2, since the current is in the opposite direction, this is minus ln 4L square by rho 2 square. This is the potential. We can calculate if we write it explicitly in terms of x and z's, this becomes x and y's, it becomes 4 pi log, in the numerator we will have x square plus r minus y whole square, x square plus y square. This can be differentiated with respect to x and y to find out the field. So the field can be calculated from this. We are not going to calculate the. So there will be two quantities. The one need to differentiate it partially with respect to x and partially with respect to y, and the field is related to the potential by this relation. So we will have I cap, j cap, k cap, del x, del y, del z, 0, 0. A of xy. In earlier case we used cylindrical coordinate system, since there were only one where, and cylindrical coordinate system facilitates calculation. In this case it will be convenient to deal with Cartesian coordinates. So this will be a contribution to the I cap del A del y. Then for j, this is the x and y components of the field and the z component is 0. Now we come to the calculation of potential, vector potential for a circular current carrying where. Recall that when we calculated the electric field due to a circular current carrying conductor using Biot-Savart law, we calculated the field at the center of the coil and at an axial point. We avoided calculation of field at an off-axial point. Here we are going to take this example. So we consider a circular current carrying wire which is assumed to lie in xy plane having radius a and is carrying a current I in anti-clockwise sense when looked down the z-axis. Everything is as usual. Our aim is to find out the potential at a point R. So this is the position vector of the field point P. We assume a length element on the circle. So this is the coordinate of R prime and this is dr prime, and our aim is to find out the field at P. So first of all, A due to a circular wire of axial point. So R is I cap x plus j cap y plus k cap z. R prime is a circle of radius a, so this is I cap cos phi prime plus j cap sin phi prime. Actually this is rho prime cap, and so dr prime is equal to a minus I cap sin phi prime plus j cap cos phi prime d phi prime. And capital R, the relative coordinate is R minus R prime. So this is I cap x minus a cos phi prime plus j cap y minus a sin phi prime plus k cap z. If we want to calculate the magnitude of R, the R square is this square plus this square plus this square. So this is x square plus y square plus z square, which is equal to R square, plus s square minus 2a x cos phi prime plus y sin phi prime. In the vector potential, the quantity that let me write it as R square plus s square minus twice a x for if R is much greater than A, if we consider the circular conductor to be a tiny conductor, a small circle, and if we are interested in calculating the field at a remote external point, then A is small in comparison with R, so we can neglect a square in presence of this, and we take R common, R square common, so this becomes 2a upon R square. R is much greater than A. So 1 by R becomes This can be approximated in binomial series. So this is 1 by r. This minus makes it plus and cancels 2. This is the expression for 1 by r. So the vector potential the only thing that we need is this one. Okay, it is there. So the vector potential at an axial point will be mu 0 I upon 4 pi dr prime. Dr prime is this much. And there will be 1 by r. 1 by r, for 1 by r we write this one. This is the field at there due to the current element I dr prime. This is actually 1 by r part. This is actually 1 by r part. This is dr prime part, and this is 1 by r part. So if you want to calculate the field, the total potential at P, then we have to perform integration over this with respect to angle d phi prime, which is missing. D phi prime was missing, and we have to integrate it. So we A at point P will be integration over over circle. This is equal to mu 0 I, this A and this R is taken common, mu 0 I A upon 4 pi R, then this and the integration over phi prime, which is a contour integration, minus I caps sin phi prime j cap cos phi prime Now we know that this sin phi prime d phi prime is equal to 0, is equal to cos phi prime d phi prime, and we further know that sin square phi prime d phi prime is equal to pi is equal to cos square. These two results we know. Keeping this in mind, we try to consider this term. When this is multiplied with this, the integration involves sin phi, which is 0. But similarly, this is 0. So the term that will survive when this multiplied with the second part. If we multiply this part, this is the function involving sine and cos, which is again 0. But when this is multiplied with this, we will have sine square. So the result is mu 0 I a upon 4 pi r, and there is a upon r square, so a square r cube common there. Now consider this multiplied by this. So this is minus I cap y prime, and the pi will be there, and pi will be there, and when this is multiplied with this term will survive. This is j cap x. This is the result. Once more, let me explain the steps. We have skipped terms. One is this: when we multiplied one with this, the integration involved either of this form, which is 0, and then we have to multiply this with this. When sine and cos, it is 0 when integrated, and cos survives, and the result is pi. So this here is pi, and this is the result. Now you see that this is the area of the circle. So area multiplied by current is the dipole moment of this current carrying conductor. So if we write m is equal to pi a square I, and the sense is along k cap, since the current is flowing anti-clockwise sense when we look down the z axis. So if we consider this quantity m cross r, this is this part. You can perform calculation, and we will be landing up to this. So this is mu 0 upon 4 pi r cube m cross r, where m is the magnetic dipole moment, is pi a square I times k cap. And the calculation of field is very easy. Note that this potential is not at an axial point. This potential has been calculated at an off-axial point. If we try to apply Biot-Savart law directly for the calculation of field at this point, it will be horribly tough. The mathematics involved will be horribly tough. But here we have obtained the potential at an off-axial point is as simple as this. And if we want to calculate field, the field will be simply minus m by r cube plus 3 m dot r times r upon r to the power 5, which is very easy to calculate. So the potential calculation here also, calculation of potential facilitates the calculation of field. As the next example, we consider again a parabolic wire, and we shall calculate the field at the focus of a parabola. So as the next example, the A at the focus of a parabolic wire, A at F of a parabolic wire. We will have a parabola in xy plane such that it carries a current I in anti-clockwise sense. It is x-axis, it is y-axis. We assume the equation of parabola to be y prime is equal to 4ax prime. We then switch over to the parametric representation, is equal to at square, and y prime is equal to twice at. So if we consider this is the source point r prime, the r prime is I cap x prime plus j cap y prime. So in terms of parametric representation, I cap at square plus j cap twice at. So dr prime is equal to taken common, 2a is taken common, I cap t plus j cap dt, and we want to find out field at the focus which has the coordinate a0. So the r is I cap a, so capital R is r minus r prime is equal to I cap a 1 minus t square minus j cap twice at. So the magnitude of r is this square plus this square, so r square is equal to a square 1 minus t square whole square plus 2at whole square. This is equal to a square 1 plus t square square. So r is there. So the if we consider this is the current element dr prime, then the magnetic vector potential at F due to this is minus mu 0 I upon 4 pi dr prime by r. The minus sign is due to the fact that dr prime increases in clockwise sense while the current flowing in the anti-clockwise sense. So this is then dr prime, this is 2a I cap t plus j cap dt upon a 1 plus t square. So a cancels out, this becomes minus mu 0 I upon 2 pi, and the quantity is I cap t plus j cap 1 plus t square dt. This is the result. If we want to find out the total potential at F, then this is done by integrating this over parabola. That is, in terms of t, this becomes note that the integration involving the x component is an odd integral, so it is 0. So the even integral part survives. So this is minus j cap mu 0 I upon pi. This 2 pi becomes pi because we change the limit of integration from 0 to infinity dt 1 plus t square. If we switch over to the condition that t is equal to tan theta, then we find that this result is simply pi by 2. So the result is minus j cap mu 0 I by 2. It is the potential at there. It may maybe we may think a bit why the field or the potential, vector potential is along minus j direction. Let us consider a parabola and 2 points. Here the current is flowing in this direction, and here current is flowing in this direction. Now the vector potential will have the same direction, which can be decomposed into 2 parts, one along this, along this. This is the x component and this is y component. Here the vector potential is in this direction, so which can be decomposed into two parts. You see the components along the x direction cancels with each other, and the component along the y direction adds up, and it is in the negative y direction. So this is this. To end our discussion on the application of vector potential, lastly we shall consider the vector potential due to a moving charge. Although a moving charge does not constitute a steady current, still people tries to apply the theory of steady current to this. A due to a moving point charge. Consider a point charge Q which is moving with a velocity v, and its position is at r prime. At a particular instant it is over r prime, and we are interested in finding out the field at r, and this is the relative coordinate. First thing is that what will be the current density? The current density J at r prime, J at r prime, so let us call it the location of Q. It will be Q v times delta r prime rq. So that is that current density is non-zero only at the location of the charge and zero elsewhere. So what is the potential A? The vector potential A is mu 0 upon 4 pi current density here B prime means entire space, Q V delta of r prime minus rq by r dv prime. The result is this is the vector potential. With this we end up our discussion on the application of magnetic vector potential to few simple cases. In the next class we shall take up magnetic scalar potential.